So, after this power hour test scheduling, so for NOC also this thermal hour test scheduling becomes a concern. So, because there are two sources of power consumption, and in a NOC, like this individual cores, so they are consuming some power in their in the test session, and also the routers are going to communicate traffic through them, or these packets through them. So, as a result they also consume power, and the problem that we have is in a SOC based system. So, if this particular core is not active for some time, so we can apply some power management technique to reduce the power consumption there. But in case of NOC, what happens is that this router and core, so they are often integrated. So, we make a tile, and in this tile this maybe at one corner of the tile we put the router. So, this is the router and this is the core. So, that way this entire thing, the power management module, so that comes for the entire tile. So, it is not for the simple router. Now, we may find that this core is idle, because this core is not being tested, it is not a part of our testing process, it is not IO pair core and all that. So, this can be switched off, or it can be put, we can do something so that power consumption will not be there. But what will happen is that these routers may be taking part in communicating some pattern that is coming from some other, from the input port or the input core. It may be going through this router to the destination core. So, the router there, it may be connected there. So, this code is being tested. So, these patterns are going like this. So, this router needs to be kept on. So, as a result this entire tile is kept on. So, that way the power consumption of this individual cores may be more in the testing mode, not because of the fact that it is being tested, but because of the fact that it is becoming a part of the whole process. So, it is becoming a part of this testing process that we have for the system. So, when we have this type of high power consumption, so there may be high power density positions in the NOC, and that way that may start consuming, that may produce a lot of heat. Okay. So, maybe it may create some hot spots, like so this is say consuming 30 watt of power, and this is say 40 watt, this is 55 watt. So, power densities may be high, as a result there may be some thermal imbalance. So, existence of hot spots may increase test time because of thermal unbalance. So, this delay of the paths will be not be correct, and also so we cannot test the chip we cannot test a portion if it is very much heated. So, what will be required is that in the entire test session we need to put some gaps. Okay. So, we need to put some time gap at which these cores will be these paths will get cooled down, the routers and cores will get cooled down, and after that only we can continue with the testing process. So, that way introduction of these gaps or the idle times in the test session, so that gives rise to the increase in the test time. Now, for the testing purpose we cannot redesign the layout. So, layout is fixed from the design angle. So, we cannot change that layout, and naturally layout is not optimized for test. So, layout is optimized for the functional operation of the system. So, whichever modules are requiring to communicate more then this layout editor, so it has put those modules close to each other. But for the testing angle, so we want to put the modules which are not consuming lot of power to close together, because because two high power consuming modules, if they are close, so the power density of that region will go up. So, to avoid it, so we have to we may like to do a layout in a different fashion, but that is not possible for the test engineer. So, that leads to higher power generation, and if there are higher power generation, the temperature increases. So, that again increases the leakage power, and that acts as a positive feedback. So, this power consumption increases significantly. So, there will be larger thermal variation. So, across the chip, so if we see, then the thermal variation will be more, and that way the delay variations are more. So, that is the problem, and we have to do something so that this hotspot can be removed. So, this the high temperature regions, they can be removed, and we can get thermal balance, and as a result the test time can get reduced. So, one possibility for doing this power and thermal reduction is the variable clocking in the test session. So, we use multiple variable clocking for thermal management. So, if we with the idea that if this clock frequency is low, power consumption will be low, as a result this temperature of the region will also go down, and if it has to be done in a region wise fashion. So, it is not that we just reduce the test clock the clock frequency of a single core, because it also depends on the neighbors. So, for the neighbors also we have to do the same thing. So, we have to assign clock we have to do this variable clocking for a region, and then the clock assigned to each core can be varied during test application. So, that is what we are talking about. So, naturally this needs a more flexible scheme. So, there must be I must have the flexibility of varying the frequency of these cores when the test patterns are being applied. So, naturally it becomes more complex. So, handling such situation becomes more complex. So, more efficient thermal management policies are required, and the extra test control mechanism are to be incorporated, so that these techniques can be utilized. So, this is a variable clock session. So, what is happening is that here we are we are testing for core 2. So, it is this clock frequencies. So, it is the core 2 is tested at some clock, and in the second case core 2 is tested at a higher clock. So, as a result its test time reduces, and after testing up to this much we increase the clock frequency of core 2. As a result it is being tested at a higher clock here. So, what happened is the core 1. So, after this point we see that the core 1 testing is over. So, only core 3 testing is going on, and it is not reaching the power limit that we have. So, we can increase the clock for core 2, so that this part can be reduced. So, this so instead of taking the time from this point to this point, so it now takes time from here to here, and this also becomes the additional testing region for the core 2. So, this rectangle is also getting added into the schedule. Core 1 remains and core 3 remains, and we see that the test time may be reduced by in this fashion. Now, thermal safe constraints are not violated, test time is reduced. So, it is if we assume that okay, this is the thermal level that we have. So, this is not violated here. So, this is fine. However, in the second case, so we have got the situation like this. So, core 1, core 2 and core 3, the original schedule was like this, and then what we try to do is that we try to increase the we reduce the frequency of this core 2 after it has done up to this much, it has gone up to this much, we reduce the frequency of core 2. As a result its time increases, but I get some facility in the power part. So, power maybe here there may be a thermal violation. So, thermal safe constraints are guaranteed. So, time is test time not compromised. So, here there may be that there is a violation in the thermal limit, because it is this core 3 is being tested at a higher frequency, and in the second solution the frequency of core 3 has been reduced. So, it is going to consume less power, and possibly it is going to ensure the thermal safety, and time is not compromised. So, T3 equal to T4. So, time is not compromised, only thermal safety has been brought into by changing the frequency of operation of core 2 and core 3. So, we can have this type of clock selection mechanism. So, the clock that is coming from the tester, it may be given to a phase lock loop, and this phase lock loop can be designed to generate different clocks f by 4, f by 2, f, 2f and 4f. Now, from the router when the test packets are coming, so this is unpacked, and the test packet itself will tell at which frequency this core will be tested. Okay. So, this is unpacked, and then the frequency is fed to the core. So, unpacked module of this network interface module. So, that is again going to be reused. So, this is in general network interface module is converting or unpacking a message a packet and forming the message and giving it to the core. The same network interface modules unpackaging module and unpackaging submodule. So, it can be used to identify for the test packet what is the frequency part, and it can be used to feed this multiplexer to select the frequency of operation for this code test. So, unpack is reused. So, test control can be carried in the packet. So, this is the thing that I was talking about. So, the test engineer might have decided that test patterns for this code should be applied on this particular clock, and all of course, for variable clocking. So, it may decide that okay, for test patterns, so T1 to T100 it will be done at some frequency, and T101 to T200 will be done at some other frequency. So, that can also be done as the packets are being transmitted. So, there may be some special packet which will identify that this is a packet for clock selection. So, when that packet comes, the NI, so it gives input to that multiplexer, so that the appropriate frequency selection part changes. Okay. So, that way these clock rates can be selected, and the test time and the power consumption and temperature that can change. So, test control can be carried in packet, and clock varies only when the test of a code is finished or started. So, this can be done. So, when a particular test pattern has been applied, so then only we can do the thing, or we can do it like this, that we divide the whole testing of a code into several sessions, and for we can define the session boundaries, and at the session boundaries only this clock changeover can take place. Of course, it otherwise there will be problem in the synchronization. So, we have got test set information for a core set C. There are NC number of cores, NI number of inputs, and NO number of outputs. We have got a set of on chip variable rate clock, so CLK signals. We have got a set of variable clock rates, a set of thermal parameters, like what is the how the what for thermal simulation. So, what are the information needed? So, they are actually the thermal parameters, like this dielectric thickness, then this the heat spreader, with the size of the heat spreader, this size of heat sink and all that. So, that we can do the thermal simulation. Then the chip floor plan and the maximum temperature T threshold. As I have said that most of the systems they have got a dynamic thermal management policy, and they have got a threshold there. So, whenever that threshold is exceeded, the system is automatically shut down. So, we do not want that in testing. So, we reach that particular threshold. So, we need to control our operation below that threshold. Okay. So, that is the maximum temperature T threshold. Maybe if that maximum threshold is say 85 degree centigrade. So, we will be operating at within say 75 degree centigrade. We will try to operate within 75 degree centigrade, being pessimistic that in actual operation. So, actual testing session, so it may become about 80 or so, but still in that case we have got a guard of 10 degrees. So, that this DTM is not invoked and the test session is not stopped in between. So, under this given this temperature threshold and all that, so we determine clock variation of each code during test application, how this clock rates will be varied, test scheduling of codes on IOs and channels. So, how on which IO port they are going to be tested, on which IO channel, and which at what time they are going to be tested. So, those parameters are to be taken, and the test application time, the objective is to minimize the test application time. So, we determine this clock variation and test scheduling of IOs and channels such that this test application time is minimized and the maximum temperature is not over this T threshold. So, as I said that this is a DTM related threshold. So, this is the problem to be solved. So, and now the rest of the thing, like how do we solve this problem. So, we have seen many such the heuristic techniques. There are many heuristic methods that have been proposed. You can also make some exact problem formulation by means of some ILP. You can use some meta search techniques. So, all those techniques have been reported in the literature, and we can take help of those methods to get this problem solved. So, we will not go into that detail, rather we will be looking into the other part of it, like how are you going to check the on chip network part, that is the components of the network, that is routers and links, how are you going to test them. So, testing of interconnect structures, testing of routers, testing of network interfaces and integrated system testing. So, unless on chip network of an NOC has been completely tested, it cannot be used to test the embedded codes. So, this is definitely true. So, first we need to test the individual routers, and once we get the confidence that the routers and links are working fine, then only we can transport the test patterns through those routers and links for to test the individual codes. So, that has to be done. So, how can we test the interconnects? Okay. So, interconnect testing has been discussed in the literature, many documents are there. They are based on one model which is known as maximal aggressor fault model or MAF. So, here what happens is that in case of NOC, we have got a set of parallel lines. Now, these parallel lines, if they are running, now out of these n lines, so we take some of the one line as victim. So, say maybe this, so if I have got say 5 lines, maybe, so this is the victim line, and what we try to see that if there are transitions. Okay. So, if there are transitions in these lines, what is the effect on this line? So, this line is called a victim line, and all these lines, so they are called aggressors. They are called aggressors. So, the effect of these aggressors will come to this victim and it will change the victim line. So, maybe that if this line is say 0, this line is at 0, but there is a transition in aggressors. So, there is since these links are operating at a high frequency. So, we have got this capacitive coupling between them. So, and also there are if it is in the gigahertz range, then there may be inductive coupling as well. So, those coupling effects, so this will have effect that will affect the logic level that you get here. So, if this line there is a rising pulse, if there is a rising pulse here, so it may so happen that this line will also be it was 0. So, it increases to some value, and after some time when it settles to 1, then it comes down to 0 and it continues to 0. So, as a result there is a glitch that is seen here. So, that way the logic level that we get at this line is not 0 for some time, but it is something else. So, this is called maximal aggressor fault model. In maximal aggressor fault model, we have got one victim line and a number of faulty lines. So, there are 5 aggressor line model, this is that thing. Then the 5 to 1 aggressor model, then there is a 3 line aggressor. So, there are only so the situation is, so there are two victim one victim line and 2 aggressor lines. So, that is also there. So, this type of models are available. So, this is affecting the this is creating crosstalk, and due to this crosstalk between the lines, so the signal levels may be inconsistent at some point. It may introduce some glitch, and also this transition time may reduce, like this, if this line is say permanently high, and this line is say permanently high, and this line tries to make a transition from 1 to 0. Now, this transition will not occur immediately because of the coupling between these two lines. So, so it will take some time. So, it may be that it is supposed to be like this. Okay, let us say it is in normal case. So, maybe the transition should be like this. So, where this is the time by which it decays to the logic low level, but due to the presence of a high signal on the aggressor line, it may take more time. So, it may be that it decays over a sequence like this. So, what will happen is that if the system is operated at a very high frequency, then it may sample the line at this point, and it at this point the logic level is still 1. So, at a destination it may be sampled as a wrong value. So, that is the problem of this crosstalk and coupling between the lines. So, and that is captured by the maximum aggressor fault model. So, the apply identical transitions to all wires except the victim line to create maximal integrity loss in the victim line. So, it is maximal. So, in this example that we were discussing, so we had taken transition in only one line. So, if you take transitions in all the lines, so if all these lines are at say logic 1 and you are trying to go from 1 to 0 for the victim line, then you can understand that this effect will even be spread over a longer time. So, that will be creating the problem further. So, we apply identical transitions to all wires except the victim to create the maximal integrity loss in the victim line. Contains 6 crosstalk errors in the victim line, like rising falling delay, for positive negative glitch and rising falling speed up. So, basically rising falling delay, that we have seen that if one of the line, all the aggressors at some voltage level, so logic high, and this victim is going to make a transition from 1 to 0. So, it takes time. Similarly, it is falling delay. So, if it is a rising delay can also occur. See, all the lines, all the aggressors are at level 0 and the victim is trying to make a transition from 0 to 1. So, it will have some rising delay. Similarly, we have got positive or negative glitch. So, as I was telling that if all these lines are making transition, so we have got this situation, and in a 3 wire model. Now, if both of these lines are going from low to high, so as a result this line will also be temporarily. So, if this line is 0, so for temporarily it will be pulled high and after that it will again go back to low. So, this duration is determined by the amount of coupling that we have between these lines. So, that is also going to occur. So, that is the positive glitch. Similarly, we can have a negative glitch, and rising falling speed up. So, this is just the reverse case, because here maybe these we have got say a 3 wire model, 2 aggressors and 1 victim at the middle. Now, all of them are making transitions like this, 0 to 1 transition. Now, ideally this transition on the victim line should say take place in this fashion. So, with this as the delay, rising delay, but due to the fact that these lines are also making transition, so it may be speeded up. So, maybe it will do it much faster. Okay, it will do the transition much faster. So, that way, that is the speed up that can occur. So, speed up apparently it seems it is not a problem, but in some cases it may create some difficulty. So, for an interconnect structure with n lines, totally 6 n faults are to be tested using 6 n 2 vector test pattern. So, this is the for the maximum aggressor fault model, it has been established. You see, there are 6 faults here: rising, falling, delay, positive negative glitch and rising falling speed up. So, 6 there are 6 possible faults, and since there are n number of lines. So, we have to have 6 n number of faults that we have to test, and for each of these tests require two vector test patterns, because first of all you have to put all the lines at some particular voltage level, then you have to apply a transition or change it. So, naturally change the aggressors and then see the victim point. So, that way it is going to take time. So, it is going the total 6 n 2 vector test patterns are to be applied for interconnects. Now, how can we do this testing for interconnect? First of all, the one possibility is the self test structure. So, a pair of test data generator and test error detector, so TDG and TEG, are inserted to each set of interconnects between 2 routers. So, this is one router, this is another router. So, these are the buffers that we have, and then this in normal operation, this from the data from this switch will go into these links. Okay. But in the test mode, this test data generator, so that will generate some test data and that will be coming to this line. So, this way this pair of TDG and TEG, they can be used for this applying this test pattern to the links. So, this is called a point to point maximum aggressor fault self test structure. Okay. So, test patterns are launched before line drivers. So, these are actually the line drivers, these buffers. So, they are actually called line drivers, and they are sampled after the receiver buffers. So, they are sampled as after the receiver buffers. At this point it is sampled at this point. highly parallel testing is possible, because you see that for every link we have got this TDG TEG pair. So, all those tests can go parallelly. So, this is a huge parallelism that we can have, but of course, with the restriction that the link power consumption, so that will go up significantly, and we can plus this TDG TEG, so they will also consume power. So, they normally they use some sort of finite state machine to generate the test patterns for testing this fault model. So, under that, so it will be taking some it will be consuming a huge amount of power. So, if the power consumption can be sacrificed, power consumption can be tolerated, then this all the interconnects in the NOC can be tested parallelly. However, that may not be the case, and we have to figure out, we have to do that in groups. Okay. So, if maybe we do testing for a part of the interconnects, and then again we repeat it for another part. So, that way it can be done.